Hi, my name is Trung Tran.
Hi, my name is Mohammed Hassan.
Hi, my name is Kenneth Berry.
Hi, my name is Gurjeet Singh, and we are Teammate. And the goal of this project was to implement the Capture the Flag game and compete with another team. For this project, we used 4 different rovers: the Sensor rover, the Flag rover, the CM rover, and the Tagger rover. I personally worked on the Flag rover, and its objective was to capture the flag, as well as avoid being tagged by the enemy rovers and obstacles along the way.
I did the Sensor rover, and its objective to detect objects, both obstacles and rovers, and to send it in a map form to the other rovers so they can avoid them.
I did the tag rover. The objective of tag rover was to tag the enemy's flag rover by getting the information from sensor rover. Once it tags the flag rover, it needs to send out a success signal to server.
I did the countermeasure rover. The function is to block off enemy's sensor rover and avoid any obstacle along the way.
So for the communication, we are using the basic Wi-Fi's. As you can see an example here, we are using these Wi-Fi's on the rovers for the communication between rovers and the server on Raspberry Pi. We are using the auto connect feature on these Wi-Fi's to increase the robustness of the Wi-Fi. We reconnect it after 5 seconds. For the message format, we are using the basic JSON. As you can see here, we have a specific start and end byte. In the examples, we are using these specific bytes as a representation of our start and end byte. There is a byte for destination and a byte for the source. For the message, we are dividing our data length into 2 halves, the upper and the lower. After that, we are actually using our data itself. We are using this checksum as to improve the reliability of the message itself. If during the communication there's a breakdown and we don't get the full message, based on this checksum, we can find that out and request the message again, or wait for another message before we send a response. There are a couple examples here. As in the first example, the tag rover is requesting the location data from the sensor rover. As you can see here, there's a start byte. S represents the sensor rover as a destination. T represents the tag rover as a source. This is our data length. Inside these brackets is the whole data itself. The message is a type request. It's requesting the location data, and the name of the rover that's requesting that data is tag rover. For the second example, as you can see, we are requesting different items from the sensor rover. There is a start byte. The destination is a sensor rover. Source is a tag rover. There is a data length, and inside these brackets is the whole data itself. It's a type request. The message contains items, MS local time, communication status, and the grid size. So as I'm the tag rover, I was using these 2 bump sensors to check the bumping into my destination. These bump sensors have only 3 pins: VCC, ground, and out. VCC and ground are always connected. Once this latch closes or something bumps into this latch, it closes this pin, setting this out to high. This bump sensor is pretty reliable because of this, because of its hardware is manufactured. We could have improved the cost, reduced the cost by using only 1 tape sensor. In our case, right now, we are using 2 tape sensors. As we can see here, we are using a tape sensor on the front and a tape sensor on the back for a better orientation, but we could have used only 1 tape sensor on the front, and using better orientation, we could have avoided using this extra sensor on the back. For pathfinding, we decided to go with the A-star algorithm. A-star algorithm uses this basic scheme of path scoring, where the final cost F is equal to the cost of moving from a point to an intermediate node, represented as G plus the cost of moving from that intermediate node to a destination node, in this case represented as H. There is an example at the bottom. There's a 3x3 grid where there is a start node in the middle. There are 8 adjacent nodes. We are representing these as some obstacles on the side and endpoint. Using the A-star algorithm, it actually finds the cost of movement from start to one of these 8 nodes. Using the lowest cost, it can find out the next point of movement inside a grid. Following through that loop, we can actually make sure that we are able to go from the start to the end byte, and that's how we are actually calculating our path using pathfinding.
I was in charge of the flag rover, and I worked on the tape sensors as well as the servo. The tape sensors that I used was the TSC 3200 RGB color sensors, and they basically have 4 different filters: the clear filter, the blue filter, the red filter, and the green filter. I originally tried to compare the clear and blue filters originally, and that the way that I did that was basically go on a 100 millisecond timer and basically check the output frequencies on how many or during that duration, how many times was it high and how many times was it low, and then I use those values and to compare whether it saw blue tape or not. I compared this on a certain field and it worked perfectly fine, but it didn't work on all different surfaces. So I tried changing my approach there, and I worked on, or I took the red readings as well, and I took the green readings as well, and I compared it to the blue. And that actually worked out much better, and it gave me better readings all throughout all different surfaces. Another reason why I chose these specific sensors was because of the LED lighting that it already has. So this really helps for different surfaces or for different in rooms with different lighting. So that basically, if there was like a little bit lighting or like higher lighting, it would still produce very accurate results. Besides just using it on just the blue tape, I used it also on the red for determining my flag. So this is actually my flag. So basically, my flag rover would basically go across right here, and it would detect that it was red, and then it would put into the flag or the grabber state, and then grab the flag. And the servo that I used was the high-tech HS645 MG. And I used the timer 3 for that as well, and I set it to a prescale value of 256 and a timer period of 6,276, and I played around with the PWM values. So again, the pulse width on how many times it was high or low, and 314 was the time or the pulse width that I gave it to have it open, and that was my initial state, and then 850 was the value that I have it for close. So basically just closes like that. The servo actually had 3 different wires. It's just VCC, ground, and a power signal, and the power signal I connected to the OC, and that's where I gave it the pulse width modulation. This specific servo, I chose it because of power consumption. It had less power consumption and rover more robust. As well as I used these specific tape sensors because I didn't have any luck with the reflective sensors, or didn't have very accurate readings. And I can show you in my demo that it worked pretty well. So right now the rover is basically just going to keep on going. It's going to pass the center zone, and I have it turn to its side, and basically it recognizes that it's outside the playing field. It was trying to find a path over there, and essentially I would send this coordinate to pathfinding and basically request a new grid from the sensor rover.
So I was in charge of the sensor rover. This rover was designed to use the TSC 3200 color sensors to follow the tape on the outside of the sensor zone and to take distance measurements every 10 centimeters. If an object is detected, it then inserts it into an array that will be used to create the map for the other rovers. To detect objects, I used 2 Max Botix sonar sensors here, the XL, and a Sharp 10 to 80 centimeter IR sensor. These sensors have a VCC and a ground input and connect to the analog to digital converter for the output. The sonar sensors output on a linear curve, and the IR sensor outputs on an exponential curve. I initially used 1 sonar sensor, but found that this was not very accurate. so I added a second to compare the values. If these values were within 5 centimeters of each other, the average is then taken and the value is what is inserted into the array. The map is then created from that array and uses a grid size of 10 by 10 in order to send the other rovers as accurate information as we can. One major issue that I ran into was using the tape sensors to stay on the tape. The sensor worked great for detecting tape, but when I tried to modify the code to stay on the tape, I ran into many logic problems, eventually adding up to 4 of them. Upon discussing this problem, I came to the understanding that instead of detecting when it was over the tape, I could have used it to detect the edge of the tape. This would have allowed for the sensor to detect degrees of tape detection instead of just on or off, and I could have used these extra modes to tell if I was wandering off in the direction of the tape or if I was wandering off away from the tape. And then I could have adjusted the path much easier. This would have also allowed me to remove 1 or 2 of those sensors and save power in the process.
Each left and right motor has an encoder attached to it. The encoder will send out an on and off value to the interrupt controller. By reading the on-off value and how often it changes, we will know the speed of each motor. This technique is called PWM, or pulse width modulation. Also, the motor will transfer out ticks whenever a certain distance is traveled. And by trial and error, I was able to find out that each tick is corresponding to about 38 centimeters. By reading the encoder value of the left and right motor, I add them together and then divided by the ticks per centimeters, I was able to get the distance traveled. Turning left and right is essentially the same as going forward and backward. I also use the encoder value and then attached to it is ticks per centimeter turn. By trial and error, I was able to find out that each tick is correspond to about 3 degrees of turning. After either the motor has traveled a certain distance specified by the message thread or turn at a certain degree, it will turn off the motor and then we'll get the other request from the queue. The limitation for the motor thread is that it was able only to get the motor object only. It cannot get any other object besides the motor object. In the control thread, each time a tape was found by the sensor, it will automatically create a motor object and tell the motor to turn or to move over specified by the requirement. My countermeasure rover will always be on the right of the sensor rover. Therefore, my countermeasure rover will always follow the left line of the tape. What that means is the countermeasure rover will try to block off the reading from enemy's sensor rover, and by moving up and down, it will further confuse the sensor of the enemy sensor's rover. As you can see in the demo, the countermeasure was able to follow the tape along the line. That is where the enemy sensor rover will maturely be stationed at, and it was able to block off enemy sensor rover from reading the accurate object. The only limitation of this implementation was that the rover, my countermeasure rover, will not be able to traverse to any obstacle placed along the way.